Hello friends, welcome to this video lectures on experimental stress analysis. My name is Avinash Parke from Department of Mechanical Engineering, Sweris College of Engineering, Pandharpur. So today we'll discuss the chapter number 6, strain measurement, that is part 2. So before moving to the part 2 of this particular chapter, we'll just take the overview of the same chapter, that is in part number 1, what we have discussed. So in the part number 1 of this particular chapter, in the previous video, we have discussed about the basic working principle and the construction of electrical resistance strain gauge. Then we have discussed about the types of strain gauges or the classification of strain gauges. So in that types, we have discussed the two important strain gauges, that is metallic strain gauges and the non-metallic strain gauges. And then we have discussed about their applications where metallic and the non-metallic strain gauges are used. Then we have discussed about the detailed construction of the strain gauges, then important elements of the strain gauges and how it works in the different types of applications. And then at the end, we have discussed one point, that is gauge factor. So the gauge factor is one of the constant parameter which we have to consider wherever we are using the strain gauges. So in that gauge factor, we have defined even definition, and by using that particular definition, we have derived one small formula, and that formula we have to use in this particular part 2 of this particular chapter. So in this part 2 of this particular chapter, we are going to discuss about the Wheatstone bridge circuit and its output, that is how the Wheatstone bridge circuit is useful in the strain gauge applications. And also we are going to derive even small derivation for the output formula of the Wheatstone bridge circuit, and that output formula is useful to check the output of all the Wheatstone bridge circuit. And after that, we are going to discuss about the different configurations of the Wheatstone bridge circuit. So there are so many configurations of the Wheatstone bridge circuit, and that configurations are classified according to the number of strain gauges used. So now in this particular part 2 of this particular chapter, we are going to study the single arm sensitive bridge circuit. Then what this particular configuration indicates, that is whatever the number of strain gauges are used in any application, so based on that particular number of strain gauges used, the different configurations are classified. Now if the single strain gauge is used in any application, then that configuration is called as a single arm sensitive bridge circuit, because single strain gauge is there. Sometimes in a single application, the two strain gauges are used, then this configuration is called as a two arm sensitive bridge circuit. Why it is two arm? Because two strain gauges are there. Sometimes in many of application, we can use the four strain gauges, so that configurations are called as a four arm sensitive bridge circuit. Like that, so many configurations are there for the Wheatstone bridge circuit along with the strain gauges. So in this particular part 2, we are going to study only single arm sensitive bridge circuit, and remaining configurations we'll discuss into the next lecture. But initially, just we'll start with the basic introduction related to the Wheatstone bridge circuit, how that Wheatstone bridge circuit is useful for the strain gauge applications, and then we are going to derive even small derivation for the output of the Wheatstone bridge circuit. Now, so whatever the figure is there in front of you, so this particular figure or this particular circuit is called as a Wheatstone bridge circuit. So if you go through this particular circuit diagram, so in the Wheatstone bridge circuit, it consists of total four arms, that is, this is the arm number 1, this is arm number 2, this is arm number 3, and this is the arm number 4. And whatever the arms are provided on that particular arms, the four constant resistors are provided. So this is the arm number 1 having resistance R1, this is arm number 2 having resistance R2, this is the arm number 3 having resistance R3, and this is the arm number 4 having the resistance R4. So all the resistors are having the same value having the same resistance value, means if the R1 is subjected to the 350 ohm, then remaining R2, R3 and R4, these resistors are also subjected to the resistance of 350 ohm. So if you go through this particular circuit diagram, so the input is given in terminal A and C. So this is that ES represents the input supply, and that input supply is given in between terminal A and terminal C, and while the output is measured in between remaining two terminals, that is that E0 represents the output, or this particular E0 represents the display of this particular Wheatstone bridge circuit, and that output, that is E0, is measured in between terminal B and D. That means out of the four corners, in the two corners the input supply is given, and in the remaining two connections or in the remaining two corners the output is measured in the form of E0. So if you go through this particular circuit diagram once again, it consists of four arms, that is arm AB, BC, AD and CD. So out of this particular four arms, the arm AB and arm BC are subjected to the same current, that is I1, while the remaining two arms, that is arm AD and arm CD, are subjected to the current I2 shown in the figure. So here in between this particular left side of this particular point A and C, so these two arms are subjected to the current I1, and the arms which are present to the right side of point A and C, which are subjected to the current I2. So this is related to the different current subjected to the different arms. Then out of the four arms, the arms which are in front of each other, these two arms are behaved similarly, and the arms which are adjacent to each other, they are not behaved similarly. That means whatever the arm number 1 is there having the resistance R1, if this arm number 1 is subjected to the tension, then whatever the arm number 4 is there in front of arm number 1, so that arm number 4 having resistance R4, it is also subjected to the tension. That means the arm number 1 and arm number 4 are in front of each other, therefore these two arms are behaved in similar manner, and we have considered it as a tension. But what about remaining two arms, that is arm number 2 and arm number 3? As the arm number 1 and 4 are subjected to the tension, so remaining two arms, that is arm number 2 and the arm number 3, these two arms are subjected to the compression. Why? Because as the arm number 2 and the arm number 3 are in front of each other, and whatever the arms are which are in front of each other, they are behaved similarly, therefore 2 and 3 are subjected to the compression, and 1 and 4 are subjected to tension. That means if any two arms which are adjacent to each other, they are behaved opposite in nature. That means the arm number 1 and this arm number 2 are adjacent to each other, but they are not behaved similarly, because one is subjected to the tension, arm 2 is subjected to the compression. Similarly, the arm number 3 and arm number 4 are adjacent to each other. This arm 3 and 4 are not in front of each other, therefore they are behaved in opposite in nature. That means arm number 3, it is subjected to the compression, and the arm number 4, it is subjected to the tension. So this is the basic construction of the Wheatstone bridge circuit. But what is the requirement of this particular Wheatstone bridge circuit? So this particular circuit is used to measure the change in resistance value. So if I have to use this particular Wheatstone bridge circuit in a strain gauge applications, so if I have to use only one strain gauge in this particular circuit, so instead of one arm, I have to attach the one strain gauge. If I have to use this particular Wheatstone bridge circuit by using the two strain gauges, so out of the four arms, on the two arms I have to attach the four strain gauges. If I have to use the four strain gauges, then instead of providing this particular constant resistance, so I have to provide the four strain gauges, and by using that particular 1, 2 or the 4 strain gauges, I have to check their change in resistance value, and that change in resistance values are useful for the further calculation. But what is the requirement of this particular Wheatstone bridge circuit? So before putting this particular Wheatstone bridge circuit in any applications, what is the requirement? The output across the terminal B and D should be 0. That means if there is no any strain gauge mounted on this particular Wheatstone bridge circuit, and there is no any load, there is no any input supply is given to the terminal A and C, as the supply is not given, means there is no any output across the terminal B and D. That means your display unit should show the 0 reading. So for that purpose, what is our requirement? We have to balance that particular Wheatstone bridge circuit. What is mean by the balancing? Balancing of the bridge circuit means there is no any output across the terminal B and D, or there is no any output across the display device. So that making that display 0, that process is called as a bridge balancing. So if I have to balance that particular bridge, so I have to satisfy this particular conditions. So if you go through this particular condition, the resistance R1 and R2 are adjacent to each other, resistance R3 and R4, these two resistance are also adjacent to each other, and by using one condition I can say that this output is equal to 0. So to satisfy that conditions, one equation I have written here, that is R1 upon R2 is equal to R3 upon R4. So what this particular equation represents, that is resistance of two adjacent arms, that is the ratio of resistance of two adjacent arms. That is why two adjacent arms, because if you go through figure, the R1 and R2, these two resistance are adjacent to each other, and R3 and R4, these resistance are also adjacent to each other, and to balance that particular bridge circuit, this condition should be satisfied by that particular Wheatstone bridge circuit. And what this particular statement indicates, that is the ratio of resistance of two adjacent arms is equal to ratio of resistance of remaining two adjacent arms. So from the figure, R1 and R2 are adjacent to each other, and their ratio is equal to R3 and R4. These two resistors are also adjacent to each other. So ratio of this particular term is equal to ratio of this particular term. If this condition will be satisfied in the bridge circuit, then your display will show the 0 reading, and this particular condition is called as a balancing of the bridge circuit. Then how it should be balanced? For example, R1 upon R2. Suppose before the Wheatstone bridge circuit is putting in the applications, and as we have made even assumptions, that is all the resistance or all the constant resistors are having the same value. That means R1 is equal to R2 is equal to R3 is equal to R4. Suppose R1 is equal to 350 ohm. As the R1 is equal to 350 ohm, remaining all the three resistors are also 350 ohm. So R1 upon R2, 350 upon 350 is equal to 1 is equal to R3 upon R4, again 350 upon 350, again 1 is equal to 1. That means there is no any output across the terminal B and D, means display will show the 0 reading. If the display will show the 0 reading before the application of load, then we can say that our above conditions will get satisfied, and that Wheatstone bridge circuit is properly balanced. Balanced means without application of load, there is no reading across the terminal B and D, means display will show the 0 reading. So this is basic construction and the working principle of the Wheatstone bridge circuit, and how this particular circuit we have to use in the strain gauge applications. But before using this particular Wheatstone bridge circuit in the strain gauge applications, we have to find out or we have to derive even small derivation for the Wheatstone bridge circuit, and in that derivations we are going to find out the formula of the E0, and that E0 represents the output across the terminal B and D. That means if input is given across the terminal A and C, then what is the output across the terminal B and D, and that formula I have to derive in the Wheatstone bridge circuit. So if you go through this circuit once again, as what they have considered, that is consider a Wheatstone bridge circuit to find out the output across the terminal B and D, and to measure that particular E0 value. I have to measure that E0 value, means I have to take the voltage difference across the two arms. So whatever the E0 I have to calculate. To calculate that particular E0, I have written that particular equation E0 in the form of voltage difference. So what is that formula? E0 is equal to V of AB minus V of AD. So what is that V of AB? The voltage across arm AB. Where it is? So this is the arm number 1. So whatever the voltage is applied across this particular arm, it is represented by V of AB minus voltage across to the arm AD. Where that arm AD is provided, this is adjacent to the arm AB. That means arm AB and arm AD are adjacent to each other, and by taking the voltage difference between the arm number 1 and arm number 3, I can measure the output voltage across the terminal E0. But to calculate that particular E0 value, or to go for the further derivation, so I have to calculate the value of V of AB and calculate the value of V of AD. So this is the basic formula which we have taken from this particular circuit diagram. Now one by one I have to calculate the V of AB and the V of AD. So initially I will calculate the V of AB, that is voltage across AB. So to calculate the voltage across AB, what assumptions I have to consider? Whatever the input is given, ES, that input is given across the terminal A and C. So that terminal A and C is common to the left side of the circuit, as well as this A and C is common to the right side of the circuit. That means while calculating V of AB, I have to consider this input supply. Similarly, while calculating this particular V of AD, I have to consider same input supply. But initially I will calculate V of AB. So for that purpose, what assumptions I have considered? That is, the input is given across terminal A and C, and by considering the left side of this particular circuit, that is V of AB is equal to I1 R1, because we know the simple formula to calculate the voltage, that is voltage is equal to I into R, that is voltage is equal to current into resistance, that is V is equal to I into R. And by using this particular basic formula, I have calculated the voltage across AB, that is V of AB is equal to I1 R1, because this arm AB is subjected to the current I1, subjected to the current R1, therefore V of AB is equal to I1 R1. And similarly, by considering one more arm which is to the left side of this particular point A and C, that is arm BC, as the arm BC is subjected to the current I1 and it is subjected to the resistance R2, therefore V of BC is equal to I1 into R2. So I1 is common for the arm AB and BC, therefore here it is also common, only resistance is different, that is here it is R1, here it is R2. But as one assumptions we have considered, that is the input applied across the terminal A and C. So if input is applied to this particular A and C, that means whatever the total voltage induced in AB and total voltage induced in BC, and if I will take the addition of AB and BC, then I will get the total input supplied to this particular terminal A and C. Therefore, from this above two voltages, I have calculated the input supply, that is input supply is equal to V of AB plus V of BC. And as value of V of AB and V of BC I have calculated, so I will get the input supply is equal to I1 R1 plus I1 R2, as I1 and I1 is common, so I have taken outside the bracket, in brackets remains R1 plus R2, and by rearranging the terms, that is I have written equation in the form of I1. So I1 is equal to ES upon R1 plus R2. That means I have kept that I1 as it is to the right side, and this R1 plus R2 I have taken to the left side. So here to the right side it is multiplied. If this particular term, if I will take to the left side, so it becomes divide. So I1 is equal to ES upon R1 plus R2. So this is the equation number 3, and whatever the equation 3 I have calculated, that equation I have to put in the equation number 1. So what is your equation number 1? That is V of AB is equal to I1 R1. So I1 value already we have calculated, which is represented by the equation number 3. So if I will put this equation number 3 in equation number 1, so I will get the voltage across terminal AB or voltage across the arm AB, that is V of AB is equal to, by putting the value of I1, ES upon R1 plus R2 into R1. So this is about the V of AB, and by rearranging the terms I have written the same value, that is V of AB is equal to ES in bracket R1 upon R1 plus R2. This is the equation number 4, and that equation number 4 represents the voltage developed across the terminal AB or voltage developed across the arm AB. Similarly, by using the same concept, I have to calculate the voltage across the AD. Why I have to calculate the voltage across the AD? Because AB is subjected to the current I1 and AD is subjected to the current I2. So while taking the voltage difference, I have to take the voltage difference of AB and AD, and already AB I have calculated, and by following the same procedure I have to calculate the voltage across the arm AD. So as to calculate the voltage across the AD, what conditions I have to consider? Whatever the procedure I have followed for the calculation of V of AB, same process I have to follow for the calculation of V of AD, because terminal A and C is common, or terminal A is common in between AB and in between AD, and by following the same procedure related to the calculation of V of AB, I will get the formula of V of AD is equal to ES in bracket R3 upon R3 plus R4. If you go through this particular equation number 4, this equation number 4 is applicable to the left side of terminal A and C, where it is subjected to the current I1 but subjected to the resistance R1 and R2. So the equation is also available in the form of R1 and R2, that is V of AB is equal to ES in bracket R1 upon R1 plus R2. This is equation number 4. And while calculating the V of AD, I have considered the right portion of this particular point A and C, because to the right side of this particular circuit it consists of current I2, as well as these two arms are subjected to the resistance R3 and R4. Means your voltage across AD is obtained in the form of resistance R3 and R4. And if you go through the equation number 5, that is V of AD is equal to ES in bracket R3 upon R3 plus R4. That means this equation number 4 is applicable to the left side of the circuit or the left side of that point A and C, and this particular V of AD is applicable for the right side of the circuit or the right side of this particular point A and C. And as we have calculated value of V of AB and value of V of AD, so I have to put this equation number 4 and equation number 5 in the E0 equation. So here we are having that E0 equation, and by putting the values of V of AB in the E0 equation and V of AD in the E0 equation, I will get the final output of the Wheatstone bridge circuit. So here from this particular term the ES is present, for this particular term also ES is present, so take that ES as a constant term outside the bracket, and finally I will get the equation, that is E0 is equal to ES in bracket R1 upon R1 plus R2 minus R3 upon R3 plus R4, and this particular equation represents the output of Wheatstone bridge circuit. And this output formula I have to use for the strain gauge applications in the different types of configurations, and by putting the values of all the strain gauges in this particular equation, I can say that which bridge circuit is more sensitive, that is either single arm sensitive bridge circuit is sensitive, or two arm sensitive bridge circuit is sensitive, or the four arm sensitive bridge circuit is sensitive. So for that comparison of all these configurations, this E0 formula is very important in the strain gauge applications, and this formula we have derived by using this particular Wheatstone bridge circuit. So this is about the basic construction and working principle of the Wheatstone bridge circuit, and then we have discussed about the output of the Wheatstone bridge circuit, in which we have derived even small formula, that is we have derived even small derivation through which we can obtain even small formula for the E0, which is equal to ES in bracket R1 upon R1 plus R2 minus R3 upon R3 plus R4. Okay, so now we'll start with the Wheatstone bridge circuit with the different configurations. So basically there are total 6 configurations are there for the Wheatstone bridge circuit, and these configurations are classified according to the number of strain gauges used in the Wheatstone bridge circuit, and as well as the number of strain gauges are behaves in which manner, whether they are behaves linearly or whether they are behaves laterally, or whether the strain gauges are behaves in tension or whether strain gauges are behaves in the compression. So based on this particular all those conditions, to total 6 configurations we have to study for the Wheatstone bridge circuit. So from that particular 6 configurations, so today we'll discuss about the single arm sensitive bridge circuit. So this is the first configuration of the Wheatstone bridge circuit, which is called as a single arm sensitive bridge circuit. So why it is called as a single arm sensitive bridge circuit? Because in the single arm sensitive bridge circuit, only one strain gauge is used in the application. That means in Wheatstone bridge circuit, out of the 4 arms, only one arm is sensitive. So if you go through the construction of the Wheatstone bridge circuit, it consists of 4 arms, and all the arms are subjected to the same resistance values. That means all the arms are subjected to the 350 ohm. But now here in the single arm sensitive bridge circuit, instead of providing the constant resistor, here on the arm number 1, one strain gauge is mounted and remaining 3 arms are subjected to the constant resistor. So but whatever the strain gauges are attached to the arm number 1 or arm AB, it is also having the same value, which is having the same value whatever the resistors are mounted on the remaining 3 arms. For example, if this resistance are having the standard resistance value, that is 350 ohm, and all the resistance should also have the same resistance value, then and then only bridge balancing is possible. But after the application of load, if the strain gauge is comes in contact with the loading, the resistance of this particular strain gauge is increases or decreases. But whatever the constant resistors are provided on arm number 2, 3 and 4, these resistors are will not change, because these are the constant resistors having the constant resistance value. But the resistance of this particular strain gauge, which is mounted on the arm number 1, that resistance is increases or decreases according to the loading. And as per the 4 arms are provided in the Wheatstone bridge circuit, out of these 4 arms, on one arm one strain gauge is mounted or one strain gauge is attached. Therefore this particular circuit is called as a single arm sensitive bridge circuit, because out of the 4 arms only one arm is sensitive, where the strain gauge is attached or the strain gauge is bounded. So for that purpose, if I have to derive the derivation for the single arm sensitive bridge circuit, so initially I have to consider one conditions, that is whether that strain gauge is subjected to the tension or compression. But already I have explained in the construction of the Wheatstone bridge circuit, always we have considered that this arm number 1 and the arm number 4 are subjected to the tension, because they are in front of each other and therefore they are behaved similarly. If 1 and 4 are subjected to the tension, so remaining 2 arms, that is arm number 2 and this arm number 3, are subjected to the compression, because these 2 and 3 are in front of each other. That means the arm which are in front of each other, they are behaved similarly, and the arm which are adjacent to each other, they are not behaved similarly. But here in the single arm sensitive brace circuit, whatever the strain gauge 1 is there, it is mounted on the arm number 1, and this arm number 1 is subjected to the tension. Therefore, if this strain gauge comes in contact with the loading, their resistance is increases, and these assumptions I have to consider while deriving the derivation or while obtaining the output of this particular single arm sensitive bridge circuit. So which conditions I have to consider? That is, I have to calculate this particular value of R1. So what that R1 represents? This R1 represents the resistance of the strain gauge 1, which is mounted on the arm number 1. So if I have to calculate this particular R1 value, so R1 is equal to R plus delta R. So what this R indicates, small r or capital R? This R represents the resistance of strain gauge before it is subjected to loading, or before the strain gauge comes in contact with the loading, and that delta R represents the change in resistance after the application of load. That means if there is no load applied, and as there is no load applied, the resistance of strain gauge also remains constant. But what is the requirement? Before application of load, the output of this particular E0, or the output of this particular terminal B and D, should be equal to 0. So if this strain gauge 1 is subjected to the 350 ohm, so at the same time remaining three constant resistors, that is R2, R3 and R4, these are also subjected to the 350 ohm. If all the arms are subjected to the 350 ohm before application of load, then your E0 is equal to 0. But after some times, if the load is applied, and after the application of load, the resistance of strain gauge goes on increasing. Why? Because it is subjected to the tension. As the resistance is increases, so their resistance becomes delta. That means before application of load, R is the resistance of strain gauge before application of load, and delta R represents the resistance of the strain gauge after the application of load. And here I have made the addition of R and delta R because the strain gauge 1 is subjected to the tension. But what about the other resistors? So other resistors are constant. Therefore, R2 is equal to R3 is equal to R4 is equal to capital R. Means if load is applied, then resistance of R2, R3 and R4 are also remains constant, because this R2, R3 and R4 are the fixed resistor. Their resistance will not change after the application of load. Therefore, the second condition is that R2 is equal to R3 is equal to R4 is equal to capital R. So these conditions I have to consider in the single arm sensitive bridge circuit. That means only strain gauge 1 or only arm number 1, it is a sensitive arm. Therefore, for the arm number 1, I have calculated the value of R1 is equal to R plus delta R, and remaining resistance are constant. Therefore, R2 is equal to R3 is equal to R4 is equal to capital R, and I have to put this particular two values in the E0 equation to solve the further equation. So we are having that particular E0 formula. So what is that particular E0 formula? E0 is equal to ES in bracket R1 upon R1 plus R2 minus R3 upon R3 plus R4. This formula we have derived from the Wheatstone bridge circuit, but in the single arm sensitive bridge circuit we are having the two values, that is R1 is equal to R plus delta R. So put the value of R1, that is R plus delta R. Again here at the denominator R1 is present, therefore R plus delta R. Instead of R2, what is R2? R2 is equal to capital R. So I have written the capital R as it is, this minus sign as it is. Then instead of R3, R3 is equal to R4 is equal to R. Therefore, R3 is replaced in the form of R. Similarly, at the denominator, this R3 and R4 are also replaced in the form of R. Then by putting these values, we will get the next equation, that is E0 is as it is, then ES is as it is. So R plus delta R is as it is. So here R plus delta R plus R. So here R plus R, it is 2 delta R or 2 dr. Therefore 2 dr plus delta R at the denominator side, minus sign is also as it is. So at the numerator here R is present, so I have written the R as it is. Here R plus R is equal to 2R, so at the denominator I have written the 2R. But here if you go through the denominator, here it is the negative sign is there. Here the 2r plus delta r term is there. Here the 2r term is there, means denominators are not same. So if I have to make the denominator, so I have to make the cross multiplication. That means by this 2r I have to multiply by r plus delta r, and by this 2r plus delta r I have to multiply by r, and after the cross multiplication I will get this particular term, that is by cross multiplication of r plus delta r and 2r I will get the equation 2r square plus 2r into delta r, this minus sign as it is. Then by this cross multiplication, this r into 2r, that is 2r square, and if this minus r is multiplied by this particular delta r, so here it becomes negative, therefore r into delta r, and as the denominators we have to make same, so at the denominator side also we have to make the multiplication, that is 2r in bracket 2r plus delta r. So at the numerator side, if you go to this particular numerator side, that is plus 2r square minus 2r square, it will get cancelled. So here plus 2r into delta r minus r into delta r, so only remaining r into delta r, so I have to return as it is by cancelling the remaining terms, that is positive negative terms, and at the denominator again I have to make the multiplication. So whatever the 2r is present outside the bracket, by this 2r I have to multiply inside the bracket, so 2r into 2r, that is 4r square, this plus sign is as it is, again multiplication of 2r and delta, it becomes 2r into delta r. So these equations I will get by cancelling the terms. Then again that e0 is as it is, epsilon s is as it is, the numerator terms, that is r into delta r as it is. From the denominator if you go through it, in this particular term r is present, in this particular term also r is present. So if I will take this r as a constant term, so if I will take r as a outside bracket, so here from this r square, one r I have taken outside the bracket, so equation becomes only 4r, plus from this particular terms only single r is there, I have taken outside the bracket, therefore only becomes 2 into delta r. So here numerator also r is present, denominator also r is present, so this r and this r I have to cancel. So then I will get this particular equation in the form of delta r upon 4r plus r into delta r. But whatever the delta r terms are present in this particular E0 equation, and whatever the E0 equations I have to calculate, that E0 equation I have to calculate in the form of k into epsilon, because from the gauge factor we have derived a one small formula, that is delta r upon r is equal to k into epsilon. If we remind this particular formula in the gauge factor, that is from this particular gauge factor definition, we have derived a one small formula, that is delta r upon r is equal to k into epsilon, and whatever the E0 values I have to obtain, that E0 value I have to obtain in the form of k into epsilon. But to obtain that particular E0 in the form of k into epsilon, so what I have to do, wherever the delta r upon r terms are present, so delta r upon r terms are present, to that delta r upon r I have to divide by capital R. So here already in this particular equation, this r and this r it will get cancelled, so for the numerator only delta r is remains, so to that delta r I have to divide by r, as that's r is divided to the numerator terms. Similarly for the denominators also I have to divide by the capital R. So for the numerator delta r upon r, for the denominator 4r upon capital R plus 2 delta r upon capital R. But as we know that from the gauge factor equation, this delta r upon r is equal to k into epsilon. So wherever the delta r upon r terms are present, so this particular delta r upon r terms is replaced in the form of k into epsilon. So our next equation becomes E0 is equal to Es in bracket, this delta r upon r is replaced in the form of k into epsilon. So at the denominator this r it will get cancelled, only 4 is remaining. Similarly here also delta r upon r terms is present, so it is replaced in the form of k into epsilon. But here one assumptions we have to consider, that is whatever the k into epsilon terms are present at the denominator, so that denominator terms we have to neglect from this particular equation. In any equation, if you will get this k into epsilon terms at the denominator, so that k into epsilon terms we have to neglect from the denominator. And from this particular equation, if I will neglect this particular k into epsilon from the denominator, so I will get the final equation, that is E0 is equal to Es into k into epsilon divided by 4, because the k into epsilon is present at the numerator, and that numerator terms I have to consider for the further calculation. But whatever the k into epsilon terms are present at the denominator, then I have to neglect it. If in any equation or in any configuration, if we will get this k into epsilon terms at the denominator, we have to neglect it. If we will not get any k into epsilon term at the denominator, so need not require to consider that effect. I have to write that equation as it is for the further calculation. So similarly, in this particular above equations, I have neglected k into epsilon term from the denominator, and by neglecting this term, I will get the final equation, that is E0 is equal to Es into k into epsilon divided by 4, and this E0 represents the output of single arm sensitive bridge circuit. That means out of the 4 arms, if only one arm is sensitive, means if only one strain gauge is mounted on the Wheatstone bridge circuit, so due to that single strain gauge, how the output of Wheatstone bridge circuit is changed, that output we have derived by using this particular first configuration, that is single arm sensitive bridge circuit. So we have discussed about the why it is called as a single arm sensitive bridge circuit, and by using this particular single arm sensitive bridge circuit, how the values of R1, R2, R3 and R4s are calculated. And by putting this particular R1 to R4 in the E0 equation, by making the denominator same, by cancelling the terms, by replacing the delta R in the form of delta R upon R, by dividing the capital R to the numerator and denominator, and by replacing this delta R upon R in the form of k into epsilon, and by neglecting the k into epsilon from the denominator, I will get this particular E0 equation for the single arm sensitive bridge circuit, which is equal to Es into k into epsilon divided by 4. So this is the output of Wheatstone bridge circuit, and like that procedure we have to follow for the 2 arm sensitive bridge circuit and the 4 arm sensitive bridge circuit. And after all the derivations, we have to compare the output of single arm, 4 arm and the 2 arm sensitive bridge circuit, and from that comparison we have to check that which bridge circuit is more sensitive, that is either single arm is more sensitive, 2 arm sensitive bridge circuit is more sensitive, and the 4 arm sensitive bridge circuit is more sensitive. That comparisons we have to made after deriving the derivations for the remaining all the configurations. So this is about the single arm sensitive bridge circuit. Remaining configurations, that is 2 arm sensitive bridge circuit and the 4 arm sensitive bridge circuit, will see in the next lecture. So in this particular lecture, we have discussed about the Wheatstone bridge circuit construction working principle. We have derived the formula for the E0, that is output of Wheatstone bridge circuit. Then we have discussed about the different configurations which we have to study in this particular chapter, and we have derived one small derivation for the first configuration, that is the single arm sensitive bridge circuit. The remaining configurations of the Wheatstone bridge circuit we'll see in the next lecture, that is 2 arm sensitive bridge circuit and the 4 arm sensitive bridge circuit. Thank you.